Good morning, everybody. I'm very pleased and honored to present my work at Tectonics monthly seminar. It's a very nice initiative, I guess, as a webinar. My name is Claudio Faccenna. I'm from the University of Roma 3. And today I'm going to show you some of the progress we've been doing during the last year to try to understand the way the Mediterranean is shaped. And my perspective is basically from the inside out, trying to underline the contribution of the mantle on shaping and controlling the surface deformation. This is a work done by a very large number of colleagues and students that participate to this long-term project. Between them, just remind you, Thorsten Becker from Austin, Texas, Francesca Funicello, and then Claudia Piromallo INGV, and Laurent Jolivet, Jean-Pierre Brown, Vicky Royden from MIT, Fabio Capitano from Monash, and many, many others that have been contributing to this long-term project. The Mediterranean is considered a tectonic puzzle, and this is due to the fact that there's two main driving large plate, Africa or Nubia and Eurasia, that are approaching each other, and between them there is a number of microplates, and we remind you Adria, for example, Iberia, Anatolia, Aegea, and Arabia, and the boundary between these two big plate is not as well defined and is diffuse over a large area, and is constituted by a number of truss and zone of suture that forming very narrow tight arc like Alboran, the Alps, Francia, Calabria, the Hellenic arc, and the Arabian arc. So the situation, the tectonic pattern is really complicated on the surface. And today I will try to quickly revise some of the tectonic, geodetic, and seismic data and model, and the main trying to convince you that this complicated pattern deformation can be indeed explained by a relatively simple pattern of mantle convection that is driving the surface deformation. So to start with, I would like just to show the frame where the Mediterranean is here. This is from G-plates reconstruction during the Neogene. The Mediterranean is here. We have Africa that is moving progressively at very, very slow rate. The red arrow here showing the path of motion of Africa towards Eurasia as reconstructed by John Dewey plate model. And fundamentally, you see that over the last 60 million years, the path of Africa have done like 600 kilometers on average, giving a centimeter per year rate of shortening and convergence between the two large plates. And this is so very different from what we have, for example, on the Pacific, where the convergence velocity and the subduction velocity always been in the order of 7, 8, 10 centimeters. So it's a completely different pattern, very slow convergence rate. So I'm now going to show you and illustrate you some of the evolution of the Mediterranean as reconstructed in a recent work we done, Vicky Royden and me, trying to underline the main tectonic feature on the evolution of the Mediterranean during the last 25 million years. So this is the pattern, 25 million years. We have the Alps. The color here show the topography. The blue is giving the ocean floor. And the light blue is a continental platform. The white blue is continent, and the red and the brown just showing different elevation of what we supposed was the mountain belt at the time. So the main tectonic feature at the time around tertiary was constituted by two non-vergent subduction zones, one below Sardinia, Corsica, and France and Spain, and the other one running on the beneath the Hellenites, where you have the continental platform subducting. At that time, the Alps was already formed, and we are consuming the last pieces of continental material here, and also we have during the embayment here the formation of the Carpathian. So interestingly, during the convergence between Africa and Eurasia, these two boundaries start retreating, and to do that, we have the opening of the BACKARC basin, for example here of the Ligure-Provençal basin that start forming around 30 million years, but the ocean floor probably start opening around 21 million years with the rotation of the Sardinia-Corsican block, and then also the acquisition of the Hellenic boundary. And progressively in time, these two trenches retreat one toward the other, trying to consuming the last piece of buoyant oceanic floor here, for example, of the Ionian Ocean, and of continental, and here in the Ligure-Provençal. The rotation of the Sardinia-Corsica block ended around 50 million years, and for about 5 million years, nothing really happened. The extensional process slowed down and shift in the Mediterranean from the Ligure-Provençal area, whereas in the Hellenic Trench, we start having the subduction of the Ionian Ocean. Therefore, we have an acceleration of the trench that is progressively consuming this floor. And also in the Mediterranean, the African boundary is now closed with probably a slab break-off. The Alps are probably desactivated completely. The Carpathian was also formed. And the Gibraltar also was escaping on the other direction. And we arrive to the present-day setting where we have the slab is discontinuous, just the northern Apennine is active on the Calabrian arc and active below the Hellenite, giving us seismicity to intermediate depth. And probably we start having some shortening along the Algerian margin down up to Sicily, and this time with a reverse polarity. Therefore, probably will produce some future deformation here. In this reconstruction, we also done a further step. We imagine what could happen in 5 and 10 million years, which is an exercise, of course, that there's a lot of uncertainties, but it's interesting to see how it may evolve the pattern. And this is a 5 million year in the future. And the situation is that probably we imagine that the Hellenic Trench and the Calabrian subduction zone may merge together and then isolating completely then the Adria plate, which is already independent from the motion of the Africa from probably the late Miocene. The other things that we imagine may occur is that we have the Algerian Provençal basin that after the shortening may initiate subduction, and has been proposed, and therefore start consuming the Algerian Provençal basin ocean, and this may lead to a new cycle of trench retreat, for example. So if you do another further step, you go in the future, we may imagine to have also a new BACKARC extensional phase. So this kind of back and forth on the polarity of subduction with opening of BACKARC extension and then further consuming, it just let us imagine towards a cycle of trench retreat phases with opening of BACKARC extension, which is really interesting and may occur only in case like that, where the convergence between Africa and the velocity of subduction exceed the velocity of convergence, which is, in this case, as we saw, very, very low. So, but what are the constraint we have on the structure of the mantle? This is a model done by Claudio Piromallo, which is here in the picture, working at INGV. Has been done some years ago, but we consider a very good model, very robust, merging together teleseismic and regional data. There are some other models that's more recent than that, but they converge on the main feature that you may see here. The tomography is showing the velocity in percentage with the reference model, and in the blue you can see the high velocity, in red the low velocity. In general terms, this is being can be interpreted either in terms of temperature or chemical composition. And it's easy to imagine that the temperature may play an important role along subduction and subduction zone, where we have cold material from the ocean that is subducting to the mantle. And this is the future that we see when we cut our model at 150 kilometer depth. So we have the Alps, the Northern Apennines slab, Calabrian, something beneath Africa, though the resolution here is not perfect, Gibraltar Arc, and then Dinorite, Hellenites, and something else. But you also may see, interestingly, some very hot, low velocity, therefore probably hot, material that is situated, for example, in Spain or in southern France and in other areas. When you go deeper into the mantle, where we see that this high velocity anomaly merge together, forming a unique subduction zone, and when you go to the bottom of the upper mantle, and 660 discontinuity, it is a huge anomaly that is spreading over the entire area, and this may be probably remind us the ocean that was between once upon a time between Africa and Eurasia, that now is completely subducted and stagnating at a 660 discontinuity. And what is very interesting here, when you compare these images, where with this old high velocity material, and so probably cold material, and you compare with what happened on the surface at 150 kilometers, then you may see that the convection have to be very active, because the cold material is down and the hot material is probably on top. Other interesting constraint on the pattern of mantle convection derived from seismic anisotropy. This is a compilation of anisotropy done from different sources. And the anisotropy is just giving us, in terms of structural geology, the maximum polarization of the waves. So gave us an idea on how the mantle is shearing or stretching, and gave us the direction of that kind of process in the olivine, probably. And this is plotted on top of the interval average velocity between 100 and 400 kilometers from tomography. So you may see where this velocity has been computed. So the first things that you may immediately realize here is the fact that on the Western Mediterranean, a lot of these SKS are aligned in an east-west direction, and also moving in this area in southern France, turning progressively to a more north-west-southeast direction. And then also in the Alps is east-west direction, and also in the Pannonian Basin. So all this area showing this east-west direction down to the Morocco and to the High Atlas. And when you go further to the east, all the pattern is basically on the northeast-southwest direction. So it looks like this pattern is pointing toward the active subduction zone of the Calabria here, and it has been proposed that material may be actually sucked from very far away from the retreating boundary that once upon a time was here and then retreated up to here. And the same may be interpreted in this way also for the Hellenic trench that was here and then retreated in this way, and so sucking material from all this area. So the pattern of SKS is actually quite simple indeed. Seismicity, I'm not going to spending much time on that, but just to remind you that the seismicity in Mediterranean is mainly on crustal depth seismicity. There is very few epicenter that go down to the mantle, and this is restricted to the Calabrian area slab, where you go earthquake down to 500 kilometers, a little bit of intermediate depth in the northern Apennine, and intermediate depth seismicity beneath the Hellenic Arc. But the rest is always only a very shallow seismicity. And you may see here the distribution of the moment tensor solution that gave us a compression over the northern African boundary here between Algeria and Morocco, and in Sicily, and also on the Alps on the eastern side, and on the Hellenic Trench, whereas in the inner part mainly it's dominated by extensional process or strike slip. GPS, as is compiled by Enrico Seppelloni on top in the picture, that compile kindly all this data on the Mediterranean area. This is two different reference frames. This is a ratio fixed reference frame showing basically two fundamental things. First of all, Africa or Nubia is moving toward Africa, basically with a northwest-southeast direction and very small rate, less than a centimeter per year. And then the motion of crustal material, the surface velocity, is changing completely when you go in the Adriatic Sea from basically Messina Strait up to the north. Everything is moving toward the northeast in a reference frame. And also you may notice the very nice counterclockwise rotation of the Arabia, Anatolia, accelerating to Aegea with a polar rotation on the Nile Delta, which is the very famous feature that has been discussed and plenty of papers. So this is also tell us that the acceleration of the velocity toward the Atlantic Trench speak about the fact that the Atlantic Trench is a main driving process here with this retreat on the overall motion. And also interestingly, this if you also do a Nubia reference frame, if you plot the same vector in Nubia reference frame, you see how there's a lot of material that is converging toward the center of the region where subduction is active. So when you look at that again, what we can see is the basic question that everybody is asking is what drives the microplate here, what produced the acceleration, irrespective of the fact that the Africa is moving in this direction with respect to Eurasia, why Adria is moving in this direction, why Aegea is moving in this direction, and what are the forces that dominate the system Mediterranean, and is the mantle convection able to explain some of this process? So to answer this question, I will revise some of the model we've been doing during the last year to try to approach and answer partly this question. But before going into that, just important to acknowledge a lot of effort has been doing on trying to modeling this process, and just remind you three of the main breakthrough that we consider important in this area. One was first done by Alberto Malinverno and Ryan in the 80s, and they were the first one to hypothesize that the trench retreat process and the curvature of the may control the tectonic evolution of the Apennine, producing the accretion on the side of the retreating trench and extension in the inner side in the Mediterranean area. So they formalized in a way the concept of trench rollback. It was already proposed by John Dewey some years before, but they applied that to a specific case like that one. This was further confirmed afterwards by the work by Vicky Royden, that she was first interpreting the very deep 4D basin formation here on the Adriatic side, and in terms of flexure of the plate, and finding that the load of the mountain is not enough to bend the plate, and so you need to have an extra load to account for the flexure of the subducting plate and to explain this deep trench that forming on the Apennine. And this also represented from and also on the other Mediterranean trenches. So this load is basically a slab pool of a buoyant, negatively buoyant material that is subducting, that is pulling down the subduction zone and producing the trench retreat in a sketch or an overall convergence frame. This is the sketch of one of her paper. And then following them also, it's important to remind that the group of Utrecht proposed Rinus Volt and Vince Pachman was producing Rob Gover's important step to an understanding the evolution of the Mediterranean, also looking deep into the tomography and realizing that the slab in the Mediterranean is not a continuous feature but is broken off in pieces, and during the slab break-off you can accelerate. Also Eugenio Carmignani was finding that accelerated the formation and unzipping the slab. And also, another important contribution, I don't have a slide here, is produced by Carlo Doglioni in his model that this global mantle flow may actually influence, and the net rotation of the lithosphere with respect to the mantle may influence the retreat velocity of the trench, that in the case of a western subducting slab may be particularly influenced on trench retreat. So this is the situation we have in the central Apennine. Just zooming here, we see if you do a cross-section from the Nice to Calabria, this is the cross-section here, you find two big deep basins, the Liguro-Provençal basin opening between 30 and 60 million, and the Tyrrhenian basin opening between 5 with the Vavilov and then 2 with the Marsilli. And this is plotted on top of the high velocity anomaly as reproduced by the tomography of Claudio Piromallo and Andrea Morelli. And on top of that, you have the age of the formation of extensional. This is the spin rift stage with a yellow box, and the blue is the age of the oceanic lithosphere. And you can appreciate that the extensional here is not a progressive feature, but jump. So you have a first phase of a spin rift deposit, then followed by the oceanic crust in the Liguro-Provençal basin up to 60 million years. Then everything stops for about 5 million years. Then extensional shift in the Tyrrhenian area at about 5, spin rift, then oceanic floor, probably even smaller than what's shown here, the recent campaign showing that it's probably smaller oceanic, but jumping to a 5 and a 2 million year. So that shows you that you have more than 800 kilometers of BACKARC extension. But it's not a continuous process, but go with the pulses. And then we can measure at least two big ones. One is the first, the Liguro-Provençal, and the Tyrrhenian. So the BACKARC process, the retreat process, is not a continuous process, but go with jump. And this is a very interesting point to explore from also a dynamic point of view. And to try to approach one of these problems, this was the work done by Francesca Funicello. We've been still working and trying to imagining what could have happened in the last 30 million years in the mantle beneath the Mediterranean. And this is, again, the image from tomography from Claudio Piromallo. And what you can do as an exercise is to restore back the position of the trench in time and to do an exercise just subtracting back and the trench retreat and the amount of subduction in time. And what we found really interesting is that the opening, the hand of the first BACKARC phase at 50 million years was corresponding more or less, and error bar, of course, with the time that the slab should have hit the 660 discontinuity. And then probably the gap of time, so we start thinking that this gap of time may be related to something deeper interaction between the slab and the lower, more viscous layer of the lower mantle. This plot here shows the amount of trench retreat in time, and this is again the Liguro-Provençal basin, the Tyrrhenian basin, and the pose. So we're going to the lab, and this is the lab that we have here at Roma 3, the Laboratory of Experimental Tectonics, and we start doing very simple experiment to investigate this kind of feature. So there was some years ago, and the idea was to take a tank and to fill it with two syrup with different viscosity, the lower one 30 times more viscous than the upper one, and on top of that putting a very thin, a centimeter thick silicon putty layer, which is a Newtonian viscous layer, denser than the underlying glucose syrup. And then we let this so it's just under the negatively buoyant of the subducting slab. And what we realize is that when the slab is falling down into the mantle, when it's approaching the lower, more viscous layer, it's decreasing the rate. This is the green box of trench retreat. Then its geometry changes, folding at depth, and then starting again retreating. And we weren't very happy at the time because we can match pretty well and scale it down to nature what was the evolution of the time. But we also realized that this time gap between the end of the first phase and the beginning of the second phase is just related to the way the mantle convect during the retreat. If you move material, if you want that for the slab to roll back, you have to move the material from this side, which is under higher pressure, and going on this side, which is under lower pressure. So you have to re-equilibrate the pressure on the two sides of the slab. And when the slab is diving to the upper layer, then this can be accounted by poloidal motion, so the material can flow in this direction. But when you seal this upper mantle cell, then the material, for the slab to retreat, you have to move material in a toroidal fashion, so laterally. And this is opening a lot of questions on the third dimension of the process and on the box that we are using, actually. So to have a trench retreat, you have to have material that may flow laterally around the slab. And this is a very important lesson after we explored that, also with a more sophisticated modeling, and this is also images velocity. You may see how the material is flowing around the tip of the slab, this time in poloidal flexure. You're looking at the lateral side. But when you look on the vertical, on the top, this is the trench. Then when the trench is retreating, you have a lot of material that's circulating along the edge of the slab, forming this vortex-like toroidal flow. And this is a very important component of this fusion. So we also reproduced that. This is a work done by Claudio Piromallo, Torsten Becker mainly, and Francesca and myself, trying to imagine how this poloidal and toroidal flexion may fractionate under different conditions and what are the boundary conditions with the viscosity jump, and exploring all this kind of feature numerically. And so, having all this in mind, we start revising our concept on the way the Calabrian slab evolved in time, and we can start from around 10 million years. At the time, we have the end of the trench retreat. This is Sicily, this is Calabria. You're looking at the trench is retreating. There was oceanic material and also a little bit of continental material already subducted in the northern Apennine and northern Africa. And at that time, you start probably having a break in the slab here. And if you do a break in the slab, then you can restart having the toroidal flow. So you make provide the possibility for the trench to roll back, and so a 5 million year accelerating and opening of the first spreading in the Vavilov, you always keep going and opening your window, and then you first produce the second spreading in the Massilic basin, and then you arrive to the present day setting where you have gap in the central Apennine and in Africa. So this tells us about the story of 10 million years of retreat, where you have a very fast disruption of a once upon a time long slab that is now reduced to a very small slab that is plunging down from Calabria just with a width of only under a kilometer. So a short-lived catastrophic event. We may imagine this process also even better. This is a work done by Valentina Magni at Oslo University, and numerical model. And the model is complicated. I can try to explain you. This is the upper plate continental. The purple is here ocean, and this is two blocks of continent. So this is an upper view. This is a side cut in the middle, and this is an oblique view. And this gave you the rollback versus time velocity. So the model starts. You have the subduction of the oceanic lithosphere here. And now I stop. The two little continents is approaching the trench. And in the middle, they have an embayment. So in this area, you can provide, you have all the time oceanic lithosphere subduction. On the side, you have continent. So this is the slab. The trench is retreating, and everything is fine. Now the continent enters in subduction. And the velocity of trench retreat, of course, is decreasing here. You have collision, small collision, and then you localize BACKARC extension, producing BACKARC spreading here. The two small continent is going down, are more buoyant than the underlying mantle, so they have difficulties, of course. And then you stop the trench retreat, so you have a phase of trench advance. Up to the moment, then you have the break of the slab, this white gap here, And in few million years, then you have another phase of trench retreat localized only here, and in few million years, you get rid of all the subduction zone. So you have just a very small slab subducting locally, and with two phases of the slab break-off. In addition to that, you have very rapid exhumation of the continental block back on the surface. So this is a theoretical model, and it doesn't mean to apply to the specific case, but just showing you that in case you have a complex paleogeographic scenario like the one we have in the Central Mediterranean, we should have expect to have a situation like that, where the slab loses continuity in few million years. So just in a cartoon-like, which is the things I like more, is drawing cartoon just to illustrate better in a simple way can be a situation. At the initial stage, the Mediterranean can be a 30 million year, was an ocean with a continental block. Then you have boloidal flow still activating, you have trench retreat, but then at the continent ocean side, you must have the first slab wreck. This may propagate very fastly, but once you get it, then you have the toroidal flow activating. And this toroidal flow itself may be responsible for the thermal and also mechanical consumption or rapid consumption and catastrophic consumption on the slab. So you have you arrive to what is the Aegean stage, a present-day Aegean stage, where you have toroidal motion. This is some of the continental plate on the side, and you can have volcanism here. Then when this activated very fast, you arrive to a Calabrian Gibraltar stage, where you're still having a little bit of subduction confined in this narrow arc. And then you arrive to the end, which is a Branchia stage, probably, where the slab is very, very small, and basically is the end of subduction. So all those kind of reconstruction provide us a very nice illustration of how can be imagined the evolution of the slab. But we don't really have an idea of how and if it's really the mantle presently, how it contributes to the deformation of the surface. And so to try to better understand that, I just collaborating with Thorsten Becker and myself, trying to converting directly in a global model the tomographic anomaly directly into temperature, assuming no chemical composition, and trying to see how and what is the pattern of mantle convection that we should expect now in the Mediterranean, and how can be influencing the pattern of the formation on the surface. So there's a lot of assumption behind this model. We're assuming incompressible flow, fluid and laminar flow, and we're using sitcom and layered viscosity, and we explore different contributions. This is a global model, but zooming to very high detail into the Mediterranean. And the most strong assumption is that they're assuming the simple scaling between velocity anomaly and density, which is maybe realistic or no, and it's interesting to see what could be the result anyway. The good thing is that we can compare the result of the model directly and in three ways with the surface deformation in terms of microplate motion, so compare directly with geodesy, with the dynamic topography, which is the motion of topography, and we will discuss later on, and with the mantle anisotropy. So I run into that quite fastly, just to illustrate the potentiality of the model and what we could learn out of that. So this is the result of one of the model. And the gray arrow is the velocity we impose, it's the velocity of Africa. The white arrow is the velocity that's resulting from the model itself. So we let Adria fundamentally and Anatolia Gea free to move under the convergent boundary and the mantle convection. And we compare that immediately with the geodetic velocity, average fixed reference frame, as we saw before. So let's just first rapidly comment in that. Interestingly, what we see is that the Adria motion from the model is actually different from Africa motion here from Nouvelle 1A. And so this is simulating the fact that Adria is independent from Africa. And in a rather, in a rather correct position. And also this model fit fairly well the motion of Anatolia, which is moving westward, at a quite high rate, but do a very bad job trying to simulating the motion of Aegea, which is actually moving toward the west itself. So, and whereas the geodetic velocity is showing that it's moving toward the southwest very strongly. But apart from the detail, I think what it could be interesting is to look at one cross-section here into the model, just to capture what's happening at that. This section goes from Caucasus, crossing Anatolia, going to Hellenic, turning to Calabria, Corsica, and then France. And so it's showing up a very large upwelling in the Near East here, beneath all Caucasus and Arabia and Eastern Anatolia, and then showing that the Mantle flow line go upwelling and then go against the trench, which is retreating. This is the Lenin trench, so it's meaning that the trench is really rolling back, is sucking material from the upper plate, but then the material is squeezing between the other trench, so it's going up again and going down again and go flat down into the 660 in the Calabrian slab and going up again in the Massif Central. So what we can realize here is that we have a very small scale convection that is on the order of a couple of 100 kilometers between the base of the lithosphere and the transition zone that provide this very small convection cell. So I think this is a very interesting result. Also because it's showing that if you have the resolution of your tomography is high enough, and if the computing power is high enough, then you can really capture a very small scale feature that we should expect operating at least over the mobile area, like all the collisional area of the western US and the area where the formation is in a mobile belt is very active for a long time. Also, you can see that this deformation, this is a cut of the slice of the model down to 250, 400, and 600 kilometer depth. And the color here is the blue is going down, material going down, the red is material going up. You can appreciate what could be the pattern of circulation and material going up and down just related to the convection and to the mantle. And also you can appreciate that this is limited really on the first between 200 and 400 kilometers, because when you go down to the transition zone, the base of the transition zone, everything flat down. Also, you can do a number of tests. For example, you can show that exactly that if you impose that the Alps are coupled, so that that's collided, this is not anymore an active boundary, then Arabia turn this way and toward the high velocity anomaly that is subducting here. But also you can do an exercise, you can stop Arabian African motion, and you can see that Anatolia is keep going westward, meaning that the motion of Anatolia can be well reproduced by the action of the upwelling in the Near East, downwelling in the Hellenites, producing that. We still have a big problem to simulate the velocity of Aegea and acceleration toward the trench, and this is maybe due to one of the big limitations of this model that has no basically crustal deformation included in with the potential energy. So it may be that the potential energy related to the crust in the Aegean may also produce an important contribution for the pattern of deformation we see on the surface. The second test that we can say is the dynamic topography. So convection produces the motion of horizontal plate, microplate, but also produce a lot of vertical deformation. And this vertical deformation is generally called dynamic topography, which is a topography transient signal related to the mantle convection that is producing stress at the base of the lithosphere, and is of course, if something is upwelling, is pulling up, if something downwelling is going down in subsidence of the surface. So we also can estimate. So we are going to show you some of the very simple diagram that we can calculate from the Mediterranean. First of all, let me show you some of the residual topography calculation. What is residual topography? The topography is the sum of the dynamic topography component plus the isostatic component. So you may always calculate the residual topography, which is the topography left, once from the actual topography, you remove the contribution of isostasy. Okay, so we take our topography, we take out what we think is the contribution of isostasy related to the crust and the mantle lithosphere, and that what is left. And you can calculate that in different way. This is on the upper level. We take, for example, crust 1 moho, that by Lask et al., and we found out what is the number here. You can see the number is here. Of course, you have to impose the density here of the mantle lithosphere and crustal lithosphere. So the assumption is very large, and probably as a function of different crustal model, and we've done this exercise to explore the different crustal model, the results are very different, of course. So it's very sensitive to the data that you have, of course. You can also estimate the free air gravity anomaly, the residual topography scaled from free air gravity anomaly directly, as in Craig et al. 2011. There you may appreciate that there are some convergence between the two different models, and particularly you can see that in the westernmost part of the Mediterranean, you see a lot of red color. So apart from the amount of residual topography you can measure, you can see that there is a large area that are not under isostasy. For example, the Iberian, in both kind of approach, showing some hundreds of meters of non-positive residual topography. The high atlas is very strong, and it's been already pointed out by several people, and also the central Apennine, and also Anatolia. But also there are areas which is probably under negative residual topography, like the Ionian Basin and other areas. So you can also do this exercise, and from our model you can estimate the dynamic topography aspect, and you can compare with the residual topography. And this is also a very interesting exercise, showing that there are some areas that emerge as with a positive signal in the dynamic calculation, and you can compare that with the residual topography and see this, for example, the Spain, also Iberia area. It's probably there is a positive residual topography and positive dynamic topography signal also in the central Apennine, etc., etc. This is very interesting, and this is I think is a very important signal, for example, to try to understand better, also from a geomorphological and geological point of view, what is happening really on the surface. For example, we expect to have an uplift in Spain and positive signal here on this area, but also in Anatolia, for example, where you have the very large plateau here that has been studied, and recent studies show a very recent uplift, and also in area where tectonic is not active anymore, so the crust is not changing dramatically its thickness, and therefore probably there is a mantle signal. So, for example, this is the study of Valerio Olivetti in Massif Central with the keep of Serenge, showing, for example, that there is a residual topography. We found a residual topography here, 500 meters, and the work of Valerio find that in the last 2 million years, for example, we have an uplift of 250 meters. So giving a rate of what is happening. And this is, of course, related to the fact that between the Massif Central, there is a well-known baby plume also resolved from tomography. But also in other areas, you can find a similar signal. For example, this is the work by Valentina Scotti here, a PhD in Roma 3, which showing that there was an uplift of the entire area in this region, and from middle Pliocene on, and an average rate of 0.6 millimeter per year, producing an uplift of 500 meters, which is very similar to what estimate from the residual topography. So in agreement with the long-term history. In the Apennine itself, it's very interesting to look at the situation because this is an active plate boundary. So, for example, we can see that the topography of the Apennine along strike showing it's pretty low in the northern Apennine, is going up in the central Apennine and going down again in Calabria, which is a very narrow piece of land between the oceans. So this is a SWOT profile showing that kind of trend. And you may compare that to the crustal thickness. So if isostasy was working, you should expect that in an area on the higher elevation, you should have a larger crustal thickness. And instead, we found the contrary, showing that beneath the Northern Apennine in Calabria, the crust is larger and a higher thickness, whereas in the Central Apennine, the thickness seems to be lower. And this is coming from a residual function of Piana Agostinetti et al. And therefore, it means that other process than isostasy or crustal isostasy is may working. And if you plot the tomography along this section running from along the Apennine, you see that, for example, in the Northern Apennine, you have still subduction ongoing, and in Calabria also. But in the Central Apennine, we probably have a break in the slab, already pointed out by several authors, that is showing that probably the presence of subduction zone may produce a decrease on the topography and also the break in the slab. So with that, we can calculate the residual topography of about 400 meters beneath the Central Apennine and negative residual topography between North and Calabria. You can also compare with dynamic topography, this time calculated. And this basically showing that if you have a slab break-off, you have uplift, for example, and presently the Central Apennine is about 400 meters out of isostasy, whereas the Northern Apennine in Calabria probably is subsides about 400 meters. So all in all, what we are trying to do is to trying to put geological estimate in our frame to tackle the problem of residual topography, and showing that actually, as very rapidly here, that many of the places where we do now have a signal of residual topography as estimate, for example, in this picture from free air gravity anomaly, we also have a very strong signal from geology, from the evolution of the last million years. And this is important because it may provide velocity and rate of deformation, which is somehow related, in this case, to the viscosity of the mantle. The last test we can do is to look at the mantle tomography, so we can compare the evolution of our model with respect to the SKS data, and the blue is where the model fit the data, the red where it doesn't fit the data. And you can see that we can have a pretty good picture of all this east-west that we found in the Western Mediterranean, saying that the suction of the retreating slab in the Calabrian Apennine is producing this signal, and similarly what happened in the eastern area. Along the subduction zone itself, you have a more complex pattern of deformation, and this is badly illustrated. Our model is not able to capture this more specific problem that is always along a convergent margin and in beneath the Alps. So you can improve your model, for example, by putting large-scale tomography and subduction zone, and here the fit is much better. So showing that the return flow producing by the retreating slab produce a good fit on the data, especially in BACKARC area. So the last test we could do is more speculative, is more volcanism. So you can plot, for example, the orogenic and anorogenic volcanism, the recent one in white and green, and the older one from 2 to 1 million years in gray and in dark green, on top of the tomography from 100 to 400 kilometer average. And this is showing the volcanism compilation from Carminati et al. And Barrier dataset. And this is basically showing pardon, that the anorogenic volcanisms do placed on top of a low velocity anomaly, whereas the orogenic one are placed on top of high velocity anomaly. And this is showing fundamentally that there is an important signal coming from the mantle and then contributing to this pattern of situation. So the region where you have a low velocity and high velocity anomaly is probably the region where you have upwelling and then decompression melting and then magmatism. So also, the toroidal flow may produce a very strong motion here, and also decompression melting and upwelling expected at the edge of the slab, and we can apply that kind of model expectation to the case of Calabria, where you have these two expected toroidal component here and two area where you expect to have upwelling, and this is actually corresponding, for example, to the case of Mount Etna. So the decompression melting we have at the side of the subducting slab may be also related to this expected toroidal flow. So we can try to sum up all our observation and with I think in the tomography again, that's gas, and with our expectation. So we imagine that the pattern of mantle convection in the Mediterranean is relatively simple. The retreat of the trench of the Calabria and Apennines slab produces suction of material that from a large part of France, Spain, and maybe also North Africa, and maybe interacting with the convection cell here in the Atlantic. But also, on the other side, we have an interaction with probably the counterclockwise rotation and flow derived from the mantle beneath Arabia and dragging Anatolia to the west and producing this pattern of situation. And locally, you can have more smaller convection cell. And then you can have the volcanism here. So this is probably illustrating the pluses where we expect to have more mantle upwelling and the minus where it's negative. So you expect two big convection cells basically all plunging down in the center of Mediterranean with a large scale return flow, one in the east and one in the west. So we can basically showing a picture like that, giving you an idea of what could be the pattern of mantle convection that is present in the mantle beneath the Mediterranean. And running to my final remarks. So I hope and I think to have shown you that the subduction in the slab, the central Mediterranean and the Mediterranean can be considered as subduction slab pool dominated system. Therefore, it means that the internal force in the system is producing all the deformation, irrespective of what is the overall slow pattern of convergence between the two big plates, Africa and Eurasia. Also, I think it's interesting to see that there is a very small scale convection cells that are restricted from the base of the lithosphere to the transition zone, and those may produce a very important small-scale convection that are producing deformation on the surface, both on the horizontal pattern, explaining the horizontal motion of the microplate, but also on the vertical pattern, explaining this large signal in terms of the dynamic topography. The amount of dynamic topography and the amount of residual topography has to be still to be constrained by the geological data. So we have two big return flow, one between Anatolia and one between southern France and Eritrea, that respond to the rollback of the two big subduction zones, one in the Hellenic and one in the trench. There are a number of open questions, a number of future perspectives in this kind of scenario. First of all, we have to be better explore what are the lateral convection connection between these two small convection cells and the larger one, operating, for example, in the Atlantic and Arabia, and what can be the influence of that. We need to have a better definition of crossal deformation. We need to have also implementing our model with including the crossal deformation, which is at the moment the potential energy that at the moment is not included in. And again, we need to better define what is the real dynamic contribution to topography to try to give more constraint to geodynamic for the geodynamic model and to see what can be the amplitude of the dynamic topography in nature. So, and with that, I would like to thank you very much for your attention. Closing with in Sicily Strait and images of what could be catastrophes during an earthquake and tsunami. And I finally end up with a number of that very short list that can help you to find all the reference and the other reference of all the picture and the text that we have illustrated here. Thanks again.